Okay, we're at 16.2 electric potential and potential energy of point charges. Um, let's share the PowerPoint. Shows a typical car battery. Uh, so it's a 12 volt. So there's a 12 volt potential. Um, and so one side is typically tied to the negative is typically tied to the chassis, and that's your 0 volts. So on the positive terminal, you've got a 1 coulomb charge carries 12 joules of energy, and as it goes around the circuit, it distributes that energy to all the external components from the battery, and then returns to the negative terminal. So let's look here on this chart. E is in volts. That's the electric field. V is in, I'm sorry, E is in volts per meter, and V is in volts. Now, what's the difference between these two graphs? Well, you can see that the V falls off at a 1/R ratio. The E falls off as 1/R squared. And we have the superposition principle, which is the total electric potential P due to several point charges is the algebraic sum of the electric potentials due to the individual charges. Okay, now here's a dipole. If you think of a positive charge and a negative charge some distance away, that's a dipole, and you can see the map, the contour map of where the positive charge is. It has the electric potential that it goes up to over 2, and the negative goes down 2. So here's the just from a single charge Q1, you at point P you have the voltage is Ke Q1 over R, and when you have two charges Q1 and Q2, the potential energy here is Ke Q1 Q2 over R, not over R squared. We're not talking about the force. We're talking about the potential energy. So it's Ke Q1 Q2 over R. So problem solving strategy for electric potential: draw a diagram, calculate and label the distances for each charge, calculate V equals Ke over Q divided by R, and then sum to get the electric potential. And so this is a little short section, and I think that's we'll stop there. Let me make sure that that's the end. Yes, section 16.3 is the potentials and charged conductors. So we'll stop it here.